Hello, everyone, and thank you for joining our live session today. My name is Larissa, and I'm an event planner at Reactor, joining you from Brazil. Before we start, I have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. The session is being recorded and will be available to view on demand here on the Reactor YouTube channel within 48 hours. Keep an eye on the chat. We'll be dropping helpful links and checking for questions for presenters to answer. I'll now turn it over to our speaker for today, so let's welcome them here to start our session.
Hello, everyone. Welcome to our session today. I'm Pamela Fox. I'm a principal cloud advocate at Microsoft working in Python advocacy, which means helping Python developers understand how to use Microsoft, Azure, GitHub, all of those technologies that you can use with Python.
Hey everyone, my name is Stephen McCullough, and I am an AI solutions architect with NVIDIA. So that means I get to work with Microsoft on implementing all the latest and greatest AI technology. To give some background about what Pamela and I are talking about today, Microsoft and NVIDIA have been in a close partnership to power the next generation of AI through deep integration of NVIDIA's accelerated computing platforms, along with Microsoft's global reach of cloud infrastructure. This webinar series is a big part of that. We want to show users, just like you, how to best leverage all of the magic of Azure and NVIDIA together. So make sure to tune in to the series. We're going to be exploring lots of cool integrations and showing you how to apply them in the real world. I'll pass it back to you, Pamela.
All right. So for today, we are talking about how we can take open weight models, specifically the GPT-OSS model, and run them using an NVIDIA NIM microservice architecture on Azure Container Apps serverless GPUs. So we're going to be mashing a lot of technologies together here. We're also going to be using the new Microsoft Agent Framework as well with GPT-OSS. So it should be really fun to see how we can combine all these technologies together so that we can run these open weight models in the cloud and have them be very powerful and very fast. So first, let's talk about open weight models. So what is even an open weight model, right? It's a little confusing because we hear the term open, and when we think open, we usually think open source code. And with open source code, everything is there, all the code that you need in order to run the software and get the same result. However, with open weight models, the thing that is open is the weights, but there's many things that can still be closed about the model, right? So the actual code that they use for training the model is typically not released. The data that they use for training the model is typically not released. So with an open weight model, you can't necessarily remake that same model. However, with the weights and with an understanding of the architecture of the model, you can run that model in order to get a new response. So the benefit of the open weight models is the ability to run those models on your own systems, on your own architecture, and be able to get a response back from the model. So it gives you more flexibility in terms of which models you can use and in what environments, right? So before open weight models, you could only use like the hosted models because you couldn't reasonably, you couldn't run any, models on your machine. You just didn't have them, right? So you can only use the hosted models, and that, that limits you, right? But with the advent of all these open weight models of different sizes and capabilities and speed, you now can pick and choose and say, okay, actually, for this use case, we're going to use this open weight model, and we're going to, run it on this hardware and, scale it this way. There's a bunch of popular open weight models that you might already be using or have heard of, like Llama, Phi, DeepSeek, Lava, Mistral, Gemma, Qwen. Lots of options. Some of these people are running on their own local machines. Some of them they're, running in the cloud. If you have a favorite open weight model, stick it in the chat and find out, what other people are interested in too. So most people know open weight models from running them locally. There's multiple options for running open weight models locally. Microsoft has Foundry Local, so that's a particularly good fit if you have a Windows machine. It's well targeted for that. There's also LM Studio, which is very popular. There's Llama File. There's llama.cpp, and there's Olama. So Olama is the one that I have. It works pretty well on a Mac, and it puts a little llama in my taskbar up here. And then from my terminal, I can actually go and I can see what models I currently have. So we can see it says that I've got the GPT-OSS model, Nemotron, Llama 3.2, Llama 3.1. These are all large language models. And you can see they're fairly small, just a few gigs. The largest one is the GPT-OSS at 13 gigs. So these are between 1 billion parameters and 20 billion parameters. And one of these is also an embedding model. So that's another option, not just LLMs, but also embedding models. So then I can say Llama run, and I'll say Llama 3.1 latest. And that will actually run it locally. So right now this is running on my machine. Let me also open up ASCII Top so you can see how it's using the resources of my machine. I like to kind of side by side it when I'm using local models so that I can see how it's working. So this is going to load up a little. There we go. So here we can see my my RAM. I only have 16 gigabytes of RAM, and my GPU. I do have a GPU, but it's not a NVIDIA GPU. On an Apple, it's a different kind of GPU, a metal GPU. Okay, so then we can go say like, okay, tell me a joke about solar system. Okay. So it's going out, and what you should see is that my GPU usage goes up. Goes up pretty high, up to like 90, 93. Okay. And now it's done. And so GPU usage goes back down. So you can really see how it's actually using my machine's resources, right? It's using up those RAM, using up that GPU, and, really using what it can in order to run that inference there. Why didn't the son go to therapy? Because he was feeling burnt out and had some planetary issues. Okay, I like that one. All right, so that's this one running locally. Now you can see I also have GPT-OSS. However, this one I cannot practically, I can't really practically run it on my machine because my machine, only has this 16 gigs RAMs and, doesn't have an NVIDIA GPU that it was, optimized for. So I did record a video of me running it on my machine just so I can prove to you how slow and painful it is. So here, this is a 15-minute video of me asking the model, let me fast forward, asking it 2 + 2. So I asked it 2 + 2, and this is a reasoning model. So it spent about 12 minutes thinking about the answer to 2 + 2. So I'll just fast forward here. This is over 12 minutes. I'll show you a little bit real time so you can see how slowly the tokens come in. It's about 12 seconds per token. And this is the kind of performance that I get, from having just 16 gigs RAM with this GPU. We're still waiting for the next token. There we go. Right. So then finally, we get through the reasoning, and it second guessed itself a little bit. This was a little painful for me to watch. I was quite sleepy at the time and nearly fell asleep while watching it. But finally, it decided to produce an answer, and we got back the single token response after the 17 minutes here. So that really shows you that with these open weight models, it makes a huge difference what hardware you're using to run the models, right? On my machine, I basically can't use this model, but on other people's machines that have, NVIDIA GPUs or that have, 32 gigs of RAM or more, they can use the model. So it's very dependent on the architecture. It's also dependent on how you're running on it, right? So here I'm using Olama. It's possible if I use llama.cpp, I might get better performance because there's all these little optimizations that go into these inference servers that can make models work better or worse. So that's a good, lead in for Stephen to talk about how we can run these GPT-OSS model using NVIDIA NIM.
Yeah, thank you, Pamela. lot to talk about here. So as Pamela showed us, you can run a model locally using Olama pretty simply. You could also run it on, a cloud server or VM if you'd like. But when we think about running a production grade, scalable, high performance AI model, it gets a bit more complicated. You need inference engines and health checks and quantization and API management and so on. There's lots of different components that go into running like an enterprise grade AI deployment. So NVIDIA really solved this problem, and they solved it by creating NVIDIA NIM. NIM stands for NVIDIA Inference Microservices. And really, a NIM takes all of the microservices you need to run AI at scale, and it encapsulates them into a single Docker image. So the benefits of that are huge. You can run it on a huge variety of platforms, from virtual machines to bare metal to Kubernetes to Azure container apps like we're seeing today. It really opens up the possibilities for what you can do with your AI models. Now, the NIM does not refer to the underlying model itself, but rather the entire package. So, for example, we have a GPT-OSS NIM. We have a Llama 3.3 70B NIM. We have Nemotron NIMs and all these sorts of NIMs for different types of models. And whenever we're talking about the NIM, it's not just the model, but also the inference engines, the observability software baked inside. It's also the CUDA packages built into the optimized image. So really the NIM is just so many different components all put into this nice, neat little package with a bow on top that you can really use for tons of different purposes. So whenever we think about NIMs, we want to really focus on the benefits that it can provide to us and what can it really do for our AI deployments. So whenever you use a NIM, you're using this package that is tuned for performance in its own specific domain. So for example, if we're using an LLM, that's going to be tuned differently than, let's say, a vision language model, a VLM, which is going to be tuned differently than a world model, or that's going to be tuned differently from a protein folding model. And NVIDIA, whenever they're creating these NIMs, goes behind the scenes and tunes them so that they are the highest performance we can get, specifically for that model and for that use case. Also, as I mentioned, because it fits in that nice package in a Docker image, you can deploy it pretty much anywhere as long as your platform runs Docker and has a supported NVIDIA GPU. And this command that I run really shows you pretty much all you would need to run the Docker container, run the NIM. So you just do a simple Docker run command, you give it access to your GPUs, you specify your shared memory, and you include your NGC API key. Now, NGC is NVIDIA GPU Cloud, and you can think of it as pretty much the comprehensive hub for NVIDIA's cloud services and software and management tools that host pretty much everything you need to deploy, optimize, and to monitor your AI and HPC environments. So you can think of it as sort of the main central place to get any software you need from NVIDIA. So once you create your API key with the platform, you plug it into your NIM container image, expose port 8000, and then you run the NIM. And just with this simple command, you can get up and running very quickly, and you have your own AI server hosted wherever you'd like. Of course, it's not just an AI server that's baked in the NIM, but also has all of these features like optimizations, observability. It exposes Prometheus metrics So it fits very well into, let's say, a Kubernetes environment. Really, it's built with production-grade, enterprise-ready standards in mind. So whenever you are working with NIMs and deploying them to production, they are very helpful for getting up and running, having a highly scalable platform, highly scalable AI deployments that are ready for production from the get-go. So this image shows pretty much just how much the NIMs support. We have over 170 different NIM types and over 40 different model types. So those are things like world models, like Omniverse, protein models, LLMs, VLMs, just a whole array of different types of NIMs that you can run. And on Azure, it fits just perfectly because you have so many different options to run the NIMs. On VMs, Azure Machine Learning, AI Foundry, Container Apps, or AKS, there's so many different ways you could run and optimize your NIMs. So I'll hand it back to Pamela to talk more about Azure Container Apps and why that makes such a great fit for NIM.
Right. So as Stephen showed, the NIMs are packaged up in a Docker container. So how do we deploy Docker containers on Azure? We have a couple different options, right? We've got Kubernetes, we've got container instances. My favorite way to deploy a Docker container is with Azure Container Apps. And it's pretty good fit for this because it has serverless GPU options as well. And we are going to need a GPU to be able to really run this, right? Like on my machine, I wouldn't be able to run the GPT-OSS NIM image, due to my machine not having enough hardware for it. But I can definitely run that on Container Apps GPUs. So for those of you who are new to Azure Container Apps, it is my favorite way to deploy any sort of application on Azure because it supports Docker files, the standard. So you're going to, define your container once using a Docker file and then deploy it up to the Azure cloud. And then Azure will serve that container, and it can do it at scale, right? So if you say, listen, this is just a hobby thing, scale it down to 0 when I don't have any traffic, you can do that. You can scale all the way down to 0, which means you're not paying any money for that container up, right? So that's great if you're just experimenting and prototyping. But on the other hand, if you're ready to go to users, go to production, you can scale, way up and say hey, you could do 200 replicas, 300 replicas, right? And you can set up these scaling rules in order to be able to handle the amount of traffic. And once again, you're only going to pay for the amount of scale you're actually using. So, I think it's a really good fit to be able to serve applications of varying scale and to be able to use this common Docker file standard. Now, when you're using container apps, there's this particular architecture that's set up for you. So first thing you have is actually container apps environment. So this is basically a virtual network that is encompassing all of your container apps. And the reason we set up a container apps environment is because it's very common to have multiple container apps, right? Like many people use microservices or maybe have one container app for the front end, one container app for the back end, right? Very common to have multiple containers running that are communicating with each other. And it's really convenient to just have them all inside the container apps environment because that's all within one virtual network from the get-go, right? So they can communicate with each other inside that virtual network and not worry about their traffic going outside of the network, right? So we've got that container apps environment as the virtual network, and it contains, one or more container apps. And then for a particular container app, each container app can have multiple revisions, right? And that's helpful because, you're going to deploy a new version of your application and it's got some changes and, you want to make sure that revision is fully able to handle traffic before you transition traffic over to it. So you'll deploy the new revision, you do the health checks on it. Once it's healthy, boom, then you start transferring the traffic over. And it goes over to revision 2. So it's really helpful to be able to have these multiple revisions up so that you can easily transfer traffic between them and, do what we call a blue-green deployment, right? And then within each revision, there are replicas, and the replicas are there in order to handle however much traffic you are, needing to handle, right? So at the minimum, it could be 0 replicas if you configure it to scale down to 0, but it could be, hundreds of replicas if you are handling huge amounts of traffic. And each of those replicas is a container, right? It's a container of the image that you specified for that app. So that is the overall architecture of container apps. Now, as I was saying, container apps now support GPUs, and the way you set that up is when you make your container apps environment, you add this GPU workload profile to the environment, which means that environment is now set up so that it can support container apps running on GPU hardware. And there is some specific regions for picking them, which Stephen will talk about later. So you have to keep that in mind when you're setting up your container apps environment for GPU. So once we've got a container app that can have a GPU, then you can pick between the NVIDIA T4 and the NVIDIA A100, and then run things like NIM on that GPU so that you can get the benefit of having access to a really powerful GPU with great memory, and being able to run small language models, run fine tuning, data science, data analytics, all those use cases, and still have all the benefits of container app serverless GPUs, right? The scale to 0 or the scale to, 1 million, right? Whatever it is that you need, and paying only for what you're using. Now, when you set it all up, typically you're also going to use Azure Container Registry in order to actually store the container image, right? So the container app will pull the image from the registry, which was defined with Docker. And now Stephen is going to show how to actually go through the full steps of deploying the NIM to Azure Container Apps with the GPUs.
That's right. So if you're anything like me, you just want to go straight in and try and figure out how to deploy this thing and not read any documentation and just figure it out yourself. But there are definitely a few prerequisites that we should make sure we have before we start deploying our GPT-OSS NIM onto Azure Container Apps. So these are the major prerequisites I've shown here. I mentioned NGC earlier, NVIDIA GPU Cloud. You want to make sure that you have an account on there and you have your API key set up. This is going to allow your NIM to pull in the correct software, the correct weights, the correct parallelism configuration, depending on the hardware that you're using. So it really helps your NIM be very dynamic whenever it has that access to NGC. Number 2, like Pamela mentioned, serverless GPUs are supported in 5 regions in Azure currently. So whenever you're setting up your environment, you want to make sure that you are doing it in one of these 5 different regions. And I have them shown here, West US 3, West US, a couple different more. And each one of them has different support for different types of GPUs. There are 2 GPUs really that you can access on Azure Container Apps, the NVIDIA T4, the NVIDIA A100. And I'll break those down and the differences between them in a minute, but just keep this in mind that there are regional requirements and regional support. So whenever you are deploying and setting up your Azure Container Apps, make sure you pick one of these environments. Third, you need to have a container registry to host your NIM so that your Azure Container App can pull the Docker image from this registry anytime that it wants to scale or just get its feet off the ground. So it's pretty simple to create on Azure, but make sure you have your container registry started whenever you start deploying container apps. So with the 2 different options for GPUs, right? When should we use either one? What's the difference? When should I consider using the T4 versus the A100? Well, to break it down at a high level, the T4 is really, really great at cost optimized inference. The A100 is more so geared towards performance. So if you see, just looking at the GPU memory, there's quite a large difference in these two different options. The T4 has 16 gigs of VRAM, whereas the A100 has 80 gigs. This is both per GPU. The A100 is based off the AMER architecture, which is the architecture that came out after Turing. So it made use of all of the different improvements and discoveries that were, implemented since Turing. Whenever we look at the performance, we do see good performance with the T4, but if performance is your main goal, I would recommend going with the A100. And if you remember at the beginning, when Pamela was running the model locally, it was hitting some issues because it was running out of memory on the laptop. Pamela had 16 gigs of memory, and the model, being GPT-OSS 20B, required more than that. So the size of your model is really a significant consideration that you need to take into account whenever you're choosing between the T4 and the A100. If you're running a smaller model, let's say it's less than 10 gigabytes, the T4 is going to run that well. But if you are trying to run a model that's anything larger than that, that's where the A100 would be your best bet. If you exceed the amount of memory available to you, then the NIM is going to provide an error saying that you've run out of memory, and to try running it in a different parallelism configuration, or try running it on a different GPU. So to sum it up, T4 is great for cost optimization. A100 is best for performance. So whenever we want to set up our configuration, there's really 3 steps that we want to think about. The first is actually pulling your NIM from NGC. In our case, this is going to be the GPT-OSS 20B NIM. But if you're running, let's say, Llama 3 70B, you would pull that NIM from NGC. Next step is to push that NIM to your container registry on Azure. So this is going to make sure that this container, this NIM, this Docker image, is available to your container app. So pretty simple to set up, and I'll show you exactly what that looks like on the code front. So I'm not going to show, the entire process of running these commands and getting it up and deployed on Azure, because that will take between, 10 and 15 minutes, which is amazing for, if you think about just going from, having zero cloud infrastructure all the way up to having your own AI model deployed on your own infrastructure in Azure. That's incredibly fast. But I want to show you just what that looks like from the command perspective. So with these 3 commands, you're really just logging into Docker, pulling that GPT-OSS 20B NIM with the latest tag. Once it's downloaded locally, you can tag it and push it to your Azure Container Registry. And keep in mind that you don't need the hardware capable of running the NIM just to download it. So you could even, download this on a Raspberry Pi if you wanted to, because it's not going to actually run the model. Just pull it, tag it, and push it to Azure. And this is that last command that pushes that container up to your Azure Container Registry. Now, whenever you want to create your container app, there's a few different pieces that go into it. The first is your container app environment. On top of that, you're going to add your workload profile, which essentially allows your container app to make use of your GPU that you selected. Whether you selected T4 or an A100, that's what you're going to specify here with this GPU type variable. And once you get your environment set up, you can deploy your container app. So a couple different things to look at here, but most importantly, we want to make sure we're passing in our NGC API key that we've been using. We want to make sure that we are using the same environment that we created in the previous step. And we also want to make sure that, if unless we want this to scale down to 0, which is like such a fantastic benefit, for demo purposes, you might want to maintain a minimum of 1 replica, just so that, in the between times when you're not using the container, if you want it to always just have 1 replica running, that could be pretty useful as well. So I like to set my min replicas to 1 and my max to 5, and that keeps it at a pretty good balance that I like to interact with it. So once you have your container app up and running, you can submit a simple health check just through a curl command. So I have it set up here. This is pretty much everything you would need. Just point it at your ACA endpoint, which is provided in Azure. So once you have your container app up and running, if you go to overview, it'll show you your endpoint. Once you plug that in here and you submit your curl command, it will return its response. And if you notice just how quick that was, and if you remember, when Pamela was showing it running locally on her laptop, it took 15 minutes to tell you that 2 + 2 = 4. And this is just because of the difference in the hardware that's available to the model. So I asked it to tell me a funny joke about the solar system, but I believe Pamela did that before. So I'm going to be a bit more specific, and I'll ask for a joke about Saturn. Let's see what it returns. So user wants a funny joke about Saturn. We need to comply with the policy. It's a normal request. Provide a joke, ensure it's humorous. I love how it thinks so logically about something that's supposed to be funny. Could be a pun, return as a joke. And then it returns the response. Why did Saturn start a band? Because it already had the best rings for a planetary hit. So yeah, it's pretty funny. It's definitely leans more towards the puns. So this is always one of my favorite health checks that I like to run. And yeah, you can get creative with it. And really, this is just the absolutely most simple way to interact with the model. But really, you can go much further and much more elaborate with the model. So to really, we're starting here at the most basic interaction with the model. Tell me a funny joke about Saturn in a simple curl command. But we can really build this up and talk about how we can turn this model into an AI agent. So what is an AI agent? Well, the way that we define it is an AI agent is an advanced AI system designed to autonomously reason, plan, and execute complex tasks based on high-level goals. So how does that work, especially with an LLM that we just saw? So the way it works is by using the LLM as sort of the brain of the operation. And there are some steps that the LLM goes through whenever it's going through that plan, tool, critique, and reason stage. So whenever a user submits a prompt to our agent, it's first going to use its reasoning capabilities to think about what tools it needs to use, what steps it needs to go through to complete this task. Next, it'll look at the tools that we provided to the agent. And this might be anything, pretty much anything you could think of could be a tool. This could be anything from, write a LinkedIn post to create and upload a YouTube video, or to search the web or find the weather. Really, your imagination is the limit for what a tool could be. And that's what makes agents, so powerful and so cool. So once it receives these tools, it will execute the ones that it believes are the best ways to achieve the task. So let's say my prompt is, plan out a day in Seattle. It will probably end up using tools to find the weather, to look up recent events in Seattle or events that are coming in the next weekend. And it'll probably use some sort of map tool to figure out where I will be and what fun locations are around me. So it will use all of those tools, and those tools will return data back to the LLM, which the LLM uses to formulate its final response. So it uses these responses from the tools in this critique phase, which is where it thinks of, how am I going to use this information about Seattle being 78 degrees and there being a concert 2 miles down the street? How am I going to turn that into a final response? And the LLM is actually pretty intelligent here. The other day, I was messing around with one of my agents, and I hard-coded the tool to always say that it was 20,000 degrees Celsius. And it actually, received that response from the tool saying that it was 20,000 degrees Celsius and said, there's something wrong with your tool. So it doesn't just take these tool responses at face value, but it actually thinks about the responses and uses its intelligence to gauge, if this is something that is an expected value. So with all of that together, this agent can return a very intelligent, very informed response. And, this is how it works with one agent, but we can also run multiple agents in what we call a workflow. So this is where you would use something like Microsoft Agent Framework to orchestrate all of your agents together, each of which have their own tools, their own prompts, their own models underneath them. And you can really just achieve incredible things using complex agentic workflows like this. And Pamela actually has some cool things to show us with how we can use agents.
All right. So we're actually going to use Python to build some agents using this GPT-OSS deployed on Azure. So I've got a repo with all the examples. So you can go and follow along with the examples and run them yourself if you have this NIM deployed. So I've got this repo open here, and you can see in my .env, I've got my endpoints. Only need one of them. So here's my NIM endpoint, and here's the model I'm running, right? So I'm running the GPT-OSS 20B and running it on this URL here. So then once I have that, I can start building with it. And I'm going to start off with just using the OpenAI Python package, which will allow us, just to basically make requests to the model. Now, when we're using this OpenAI package, we generally have two ways of interacting with models. We can either use the chat completions API or the new responses API. And for the GPT-OSS model, we really want to use the responses API. That is what it was designed for. That's what the reasoning works well with. And you're just not going to get good quality responses from the chat completions API. So in all the examples, we are using the responses API. And that means that we're using client.responses.create instead of client.chat.completions.create. So that's the first point I want to make, is that this is going to depend a lot on the model, right? If we were using that Llama 3.1, then we'd be using the chat completions API, because that one wasn't actually designed for responses. But for GPT-OSS in particular, we want to use the responses API. So here we say, all right, we're going to get more specific about the Jupyter. Okay, seeing how incredibly corny these jokes can be. So we're
I don't think this model was trained on jokes or on humor. They left it out of the training data set.
The jokes are just so I think the Llama 3.1, if you want jokes. So why don't scientists ever give Jupyter away as a pet? Because even if you promise to feed it a little gas, it'll still dominate the fetch game. It reminds me, my 6-year-old was reading this Star Wars dad jokes book last night, and she finishes reading, and then she's like, well, that was really boring, but I read it. Good job. All right, so here we go. So that's the basic response. Now, the next thing we want to do is make sure we can use the reasoning ability of the model. So there's two aspects of that. One aspect is that actually when we're using a reasoning model, we can specify the effort of the reasoning. So here I say reasoning effort low. So this can either be low, medium, or high are the three options here. So I'm going to specifically say low here. And I'm giving it a bit of a trickier question that requires more thought. It's like, okay, if we offer free bike rentals, how is that going to affect commute? Something that's worth thinking about instead of a joke. And then when we're parsing out the response, now when we're going through the response, we're going to check to see, is this a message, like the actual response from the model, or is it a reasoning content, right? So is it what the model is outputting as its reasoning tokens? And then we can display them differently, right? So if we were doing a user-facing application, you can choose to show the reasoning. And that's kind of nice. It gives the user some insight into the model's process, and also just helps with perceived latency, because reasoning models tend to be slower. And if you add the reasoning output to the UI, it's going to make the user feel like something is happening, right? Let's go and run that and see what kind of response that we get here. And see what, okay, so this is a much longer response, but let me see if I can find the reasoning. All right, so the reasoning was super short, right? It just says, need to discuss varied durations and locations impacting community behavior. So the reasoning was literally a sentence, right? And then the response is actually quite long, right? Now let's try changing that to high. All right, let's go all the way up. And this will take a bit more time because it's generating more tokens. And since I'm not streaming back the tokens, I have to wait for the entire response to come back. We could change this to stream back the tokens. Once again, if you're making a user-facing application, best practice is to stream back the responses from models in order to reduce that perceived latency. So here we go. It's still going, still thinking real hard here about its response. And I remember seeing when the GPT-OSS model was launched, and when they did the benchmarks for the model, they looked at how it performed on like various exams and like all these exam question benchmarks, and they definitely got better results when they set the reasoning to high. And the amount of reasoning for like a single exam question, it was like kind of like an AP bio exam question. It was so long. It was like pages and pages of reasoning to try and figure out the AP bio exam answer, right? All right, so here with this one, scrolling. Okay, so here, this is all of this is going to be reasoning. So you can see reasoning high is it's high. It's a lot. So there's really a big difference between reasoning, still reasoning. Oh God. All right, we got it. All right. So there is a huge difference between reasoning low and reasoning high. I'd probably recommend medium for a good, good medium response there. But it's something you want to evaluate for your use case, right? Like you might only need low, and that's great because that's going to be faster and less token use. But if you're doing something, really difficult, you might find you get better responses with high. Okay, so now we've figured out how to use responses with reasoning, effort, and showing those thought process. So the next step is using the tool calling ability of the model. So what was significant about GPT-OSS is that it's both a reasoning model and it can call tools. And that's what enables us to use it for agents, is that ability to call tools. So this is also known as function calling. The idea is that we give the model a bunch of tool definitions and we say, hey, model, these are the tools you can call. Each of these is like a function that has a name and has some arguments. And then the model decides based off of the tool definitions and based off the user query, whether there's any function that's going to help in answering that query. And then it'll say like, okay, I think you should call that function, right? And then in our application code, based off what the model decides, then we're the ones that actually call the function. If you do want to understand better how function calling works, we just had a live stream that we were this morning where we spent an hour on it. So you can watch that recording if you want to get really deep into function calling. We're just going to do it more quickly here today, but let's go ahead and send this off. You can see I'm asking, what is the weather like in Paris today? And I sent it a single tool, which is the get weather function. And so we can see the reasoning. It says, oh, we need to call the weather function, use the function name with location Paris. And then it says, okay, you should call this tool with this location, right? And so then in my code itself, then I would actually call the function, right? I'd be like, okay, if the item name is get weather, then I'm going to load in the arguments and actually call the weather and then send that information to the model. So the next step is once we can, see that we can, get the model to suggest a single function call, then we advance to doing function calling in a loop. So here we have multiple functions. We've got lookup weather and lookup movies. And we have the actual implementations here. These are not very fancy implementations. You would actually be calling an API here and here, right? But in this case, we're just going to return back some objects. And then, we've got the user question, is it rainy enough in Sydney to watch movies and which ones are on? So this question requires calling multiple functions, right? First, we need to check the weather. Then we need to check which movies are on. So hopefully the model is going to realize that and be like, okay, all right, first check the weather. Okay, great. This is the weather. All right, now go and check the movies. And sometimes the order matters. Sometimes it doesn't, right? The model will just realize like, oh, okay, this is what I need to do next, right? So what we do is, we go through, we get back the responses, we call the actual model, and we send it all to the LLM. So there's a lot of code involved there. Once again, if you want to understand it more, we did have a whole stream about it this morning. But you can see that, it says we should look up weather first. Then it says we should look up movie. Then we actually execute them. And then we get the details. And then we get the final response here, right? So it says there's enough rain to make cinema a comfy alternative to braving the streets. And then we get the actual movies there. So the ability to call multiple tools in a loop, this is the basis of agents. Once we see that a model is able to handle multiple tools in a loop, then we can start building agents on top of it. And at the point where you want to start building agents, that's where you probably want to bring in an agent framework, right? So today we're going to use the Microsoft Agent Framework, which is the new framework that just came out, which is the replacement for Semantic Kernel and AutoGen. It's the successor to them and has the best of their features together. So we've got a bunch of examples here with agent frameworks. You could also use the OpenAI agents framework. I've got the same examples in both of those. But you do need to have a framework that works with the model, with the architecture that you're using, right? So I did try some frameworks that weren't actually compatible with this endpoint, and and I wasn't able to show. So definitely when you're using an open weight model and you're thinking of using a framework, you really want to test out the framework with the model to make sure that it really, really works well with the model. All right, so now let's try actually using the agent framework, okay? Now that we see it supports tool calling, so we're gonna go to the agent framework. And here, we bring in the agent framework and we connect to our NIM endpoint. And here we've got the get weather function. And then we create an agent and say, all right, this is the agent, here's your system prompt and here are your tools, right? And then we say agent, all right, so how is the weather today in San Francisco? So these agent frameworks make a lot easier to call tools and especially call multiple tools. So he says, all right, in San Francisco, it's a cool 60 degrees Fahrenheit. Okay, so that works. So let's get fancier, right? So now we can get multiple tools. So here we have a get current date function, which is really handy for agents to be able to find out. we have a get activities function, and we have a get weather function. So we're going to give all those tools to the model and ask it, what can I do this weekend in SF, right? So hopefully it's actually going to call all three of those functions in order to figure out what's appropriate, right? So we can see first it gets the current date because that's the first piece of information it needs. Then it gets the weather for that date. And then it gets the activities, right? And then it says, all right, based off the weather and the current activities, here is what you should do, all right? So that's working really well there. And so you can see how the GPT-OSS model, even though it's a smaller model, it was able to figure out the right order to call these tools in, the right arguments to pass in, so that it could fully answer this question. Now we could move on. Let's move on to using this with MCP, because I did see a comment about MCP in the chat. So we might be using our model with with MCP server. The first thing we could use it with is an actual deployed MCP server, like a public one. So for example, Microsoft Learn has an MCP server here at this URL. And so we're like, okay, we have this MCP server. We want our agent to be able to use all the tools from that MCP server. So we're just going to ask a question from the documentation. Does Azure offer serverless GPUs? So let's see if it can use that Microsoft Learn documentation server in order to answer this question. And then that server has 3 different tools. One of them is for browsing the docs or searching the docs. The other one's for searching samples. I don't remember what the third one's for. But okay, it already completed and was able to answer the question. And we could get a little fancier, ask for citations. But it's really nice that we can just point at one of these servers. Now, if we're running this like a model on our private infrastructure, we might actually want to be running a local MCP server. So to do that, here I've got just a sample MCP server that I can run locally, and this is a server for hotel booking, right? So it's got some tools in it like suggest hotels, and so I can just run this locally, here on this machine, and then I've got this code here, and I can just point it at the local server and say, all right, you're going to, look for a hotel. So we can run that, and it can, call the tools. And this has an exception. All right. I think I have to dig into this. This might be with it's not liking. This might be because it's running on code spaces. Okay. All right, so I'll have to dig into that networking connection. It's something with the ports within this environment here. But generally, you can point these agents at tools that are running off MCP servers, tools that are defined in your code, so you can hook them up with different APIs. And what I'm really impressed about is the fact that this is all working with GPT-OSS, and GPT-OSS is only a 20 billion parameter model. That is not many parameters at all in the scheme of things, right? Like the models that we're using day to day, like GPT-5 are, way bigger than that. They don't even document how big they are, but they're much bigger than that. So the fact that we can use the GPT-OSS model on NIM in order to, interact with many tools in order to answer questions is really cool, really impressive. So now let's talk briefly about productionizing. So you play around with this, you're like, oh, wow, this is actually like working. This is going to be really nice for our scenario where we want to run some open weight models. So what should you be thinking about? The first thing you want to think about is security, right? Here I am using a public endpoint. So if any of you were fast enough to, write down these endpoint URLs, then, you could be hitting up my endpoint and using my GPU, right? So that, is an issue because you don't want people to be able to use your infrastructure and for you to get charged for it. If you do, good luck. I'll take this down pretty soon too. But generally, you don't want to just have a public endpoint available on the internet unless you really want that, right? So what you often want to do is actually use private networking and only hit up that endpoint from within your virtual network, right? So you can, when you're configuring your container app, you can decide what the networking is going to be, right? You can go to the let's see, we can go to the container app and then open up the networking tab here. Networking. Here we go. So there's the ingress tab here. And you can see how I've set this one to allow ingress and accept traffic from anywhere. But as you can see, I can customize this, right? I can limit to the environment, can turn off ingress entirely, change the type of ingress, transport, certificates, target points, IP restrictions, lots of things that you can configure. And you can also set up your own custom virtual network as well. If you want to set up, like network security rules using subnets and network security groups. The next thing you might consider is how could you secure the endpoint with key access, right? Here I'm, not really passing in a key at all. I'm just saying API key none, and it's not checking the key. But if we wanted to, we could maybe, define a key and we could store it either in, the container secrets. There's a special way of having secrets. You can see this one references a secret. So you can store in container app secrets, which is down under here, security secrets. And here we're doing the NGC API key, but we could separately have an endpoint key and protect it behind that key. We could also get fancier and put API management in front, Azure API management. And so there you could set up keys. You could have multiple keys. You could have a developer portal. You could do set up cores, do rate limiting, do throttling, headers, all sorts of things you can do with API management. So that's something to keep in mind if you really want to have a high amount of control about how you distribute this endpoint. If you've got multiple, developers using it, especially external developers. The next thing you want to think about is your capacity. Will your, your GPU be able to handle the amount of traffic you're going to send at it? So as I mentioned, with these containers, we can scale them. So here's the scale tab here in the portal. You can see I've got mine set min 1 and max 10. We could set this back down to 0, but if we're going to actually put this in production, we're definitely going to have a min of 1 or maybe higher. You can see it's a max of 1,000 replicas here. And then you can set up custom scaling rules. So the default one is HP scaling based off of 10 concurrent requests. So, once it gets, 20 concurrent requests, it's going to start up a new replica, right? And if you want to really verify that, what you can do is set up a load test. And that's always the best practice before you tick something in production, is to set up a load test. And you can use Azure load testing to set this up. So I've got an Azure load testing set up here in the portal. And Azure load testing is a way that you can run load tests on Azure infrastructure. So that's nice because you can actually simulate loads coming from, different geographies, right? If you want to make sure that you can handle, a bunch of Australia traffic at the same time as a bunch of Brazil traffic, you can actually simulate that in Azure load testing, right? So it's a nice thing to use. So here we can see tests that I've run in the past, and we can go through and see, okay, so this one was 47 virtual users, and this was run by my colleague, Anthony, who's doing the stream later today. And, for each of them, we can look at, how many users we got, the requests. We can even see how the replicas increase. So here it went from 2 replicas to 4 replicas as the number of requests went up, right? So as we got, this many requests, then the number of replicas increased here. So that is a really important thing to do before you're going to take something into production, to make sure you can really handle the capacity. All right. So those are the big things we wanted to share today. Now, if you want to try this out yourself, we do have a tutorial that shows you how to deploy a NIM to container apps. That tutorial uses Llama 3, but if you want to try GPT-OSS, you just swap in GPT-OSS in the tutorial. And you can basically, any model that you can find in the NGC catalog, you can swap in and try deploying it to container apps following that tutorial. And we also have upcoming sessions in November where we're going to be talking about model performance and how you can benchmark your models and ideas for improving the performance even more after you've done benchmarking. So if you do want to learn about that, you can register for the series and join for November. We also do have one more version of this stream happening today for folks in Australia who are still fairly asleep right now, maybe just waking up. So if you want to tune in when you're more awake, well, Australia, APAC, the whole region, China, Japan, Malaysia, wherever you are in the APAC region, in another 7 hours, we'll have that stream as well, covering the same topic from today. So that's what we want to cover. I do see there's a question in the chat. We actually had a couple of questions that maybe Stephen could help with. So one question is, what session layer protocol are the GPU servers on?
I saw that question, but I can't say I totally understand the question. Are you talking about the OSI layer?
Yeah, I assume they meant like the OSI stack as well.
I figured.
This one, OSI model.
Yeah. The classic. Yeah, so that's such an interesting question, because really it depends on how the GPU is being used. Whenever you're using the GPU just directly to a CPU, that's going to be going across what's called NVLink, or it could be going across PCIe, which is going to be those lower layers of the OSI stack. So think about the physical and the data link layer. But if you are doing something, let's say, with large scale clusters where you have, just a massive box of GPUs, let's say, in a DGX, that's when things get a little more complex and we start to use, higher layers of the stack. So lots to unpack there. I definitely recommend, reading some articles about that, because it is really fascinating.
All right. Yeah, I need to learn more about that. I didn't understand all the terms you just said. So that's great. Yeah, if we have any particular article links, that would be good to share. We also have Robert asking for a link to the tutorial. So let me get that link. Here we go. It's right here. And we'll stick this in the chat. So this is the tutorial on learn about deploying here. There's also a question, can NIMs be community made? Could I create my own container leveraging the NIM utilities and benefits and swap the models for a fine-tuned or LoRa adapted model?
Oh, where's that question?
Just came in from Hector.
Okay, I see. Can NIMs be community? So what you can do is you can create your own container. Whenever you create your Docker file and you say from a specific base container, you could specify a NIM container as the base container. And then you could, edit your own files or do what you'd like. Big asterisk there that it's not going to be you're not going to have all the same guarantees and support as you would if you were just using that raw base model. But yeah, you could absolutely, start with that and put in whatever you want into the NIM and deploy it if you'd like. It's a great experience to learn about, how the NIMs work and what exactly is going on inside them. I've spent a lot of time exploring all of the different, files and software used to run the NIM. So definitely, I recommend checking it out.
Awesome. There was also a question whether you could run this on a phone that has an NVIDIA GPU. Have you tried that?
I have not tried that. That is such, wow. I would love to try that though. I don't have a phone that has an NVIDIA GPU. I can't say I'm too familiar with the mobile market. But, if you have a phone like that, definitely give that a shot and, maybe send me a message on LinkedIn.
All right. Awesome. We are over time. Thank you so much, everyone, for the questions. If you do have any follow-up questions, bring them to our stream in 7 hours, or, just find us on the internet, and we're happy to chat more. So hopefully we'll see you at future streams. And, for this series or any of our other series, as I said, I do also have a stream tomorrow digging more into agents and the agent framework. So if you are keen to learn more about agents, join us for that stream. And we also have one about MCP servers on Thursday. So that could be interesting to you too. So thank you, everyone. We'll see you next time.
Thank you.
Thank you, Pamela. Thank you, Steven, for the session today. Thank you all for joining us. We are always looking to improve our sessions and your experience. So if you have any feedback for us, we would love to hear what you have to say. You can find the link on the screen or in the chat, and we'll see you in the next one.